forced us to shut down most of the emission source, we saw a natural experiment. And during that time in India, we have seen, and there are a number of studies which have already published, demonstrated that because of that shutdown, we have seen significant decrease in pollution level at various scales in northern India. And this is just an example where we have seen lowest aerosol observation over Indo-Gangetic Plain in last 20 years data records from the one of the MODIS satellites. So this kind of natural experiment really give us a very clear picture that this is cleaning air is doable if we can control the emissions. So when we talk about the air quality monitoring, there are three main components. Traditionally, it has been done using ground measurement. We have this instrument which makes measurement at the ground and provides in different temporal resolution data. Then we use the model for a long time to understand what is happening in the atmosphere, or to forecast what is going to happen tomorrow or day after tomorrow. And then in the last 2 decades, increasingly we have started using observation from the satellite. So in current time and going in future, what I feel is these three will be an integrated part of air quality monitoring or management system, and they can provide a complementary information to understand what is going on in terms of air quality in the atmospheres and at the surface where we breathe. So just looking some of the long-term trends in or the climatology, we have 20 years of data records from two of the MODIS sensors, which flies one in morning, one in the afternoon, and one of the parameter which it provides is called aerosol optical depth. It represents a columnar loading of aerosols in the atmosphere. So it's not at the surface, but it can be used as a proxy for surface particulate matter. So what you see on the left is mean aerosol optical depth at district level for those 16 years, 2003 to 2018. And what you see is the highest level is across IGUP region. But if you look on the right side, these are kind of trends in aerosol optical depth. And this is over all the 16 years. So you will see that the IGPP, although has highest AOD concentration, but the trends are very alarming in southern and central India, where they have been changed by a factor of 2 to 3 in places due to various increased emission activities. So this is very, very important to understand that often we focus too much on IGUP region and it for the right reason, but there are other parts of India which needs more attention. Now, when it comes to the agriculture burning has been one of the hot topic, and it does produce significant emission and impact the air quality during certain time of the year. So what you see here is again those 16 years of fire data from the MODIS, which has ability to detect the fire. And what it provides is on the left is the maximum fire counts on a given month. So you can see that Punjab and Haryana and some of the other states have the highest number of fire count detected by that can go up to 10,000. When you see in terms of the season when these fires are happening, the center panel shows the month corresponding to those maximum fire counts. And again, we can see in the northern India, mostly everything, all the fires are happening during post-monsoon. Now remember, these are not only agriculture fire, there are some forest fires also, or open grassland fires as well. But most of them are represent agriculture fires. Whereas in southern and central India, those peaks happens during the spring or the early in January to April time frame. Again, if you look the trends in those fires, we will see that the same belt where we were seeing the high aerosol optical depth concentration or the more trends in AOD, we'll see the number of fires have been also going exponentially increasing in that part. So this is very, very critical to understand, although this doesn't support that all of that increased AOD is because of this fire increase. There are other sources which are playing a role here, but this can be one of the factor. Now let's put in terms of the emission, because air quality is related to the emission. The fire count is kind of give some uh, a way to actually see how much fires are burning, but it's not really going to tell you about the emissions. So in order to get the emission, what you see here on the left is the CO2 emission in terms of the metric tons on the x-axis, on the y-axis, and then you have the number of all the lines represent different years, and then this is for 2009 up to 2019. So what you see here is that the red line shows the 2019 and the black line shows the mean. So in 2019 we had significantly lower emissions compared to the median from the last 15 year or so. And then also we saw that on a daily, which is shown on the secondary y-axis, we saw the two peaks. One is before the Diwali season, and second one is on the next to the Diwali season. So Diwali festival. So I think these kind of shows typical cycles of agriculture burning, which happens in northern India during this time. But if you just put this in a perspective comparison, then this CO2 emission is kind of indicator of how much is emissions are happening from these fires. So this is about 10 megaton. And if you compare that with the annual emissions in India from the fossil fuel, then it is about 2,500 megaton per year, which is, so this brings down to about like a 0.5%. So it's not a big contribution in terms of the total emissions. Now let's see what is happening in the 2020. This is there have been a lot of news that 2020 has seen more fires, and in a part that is true. So this what you see on left side is October 1 to 18 number of fire counts from 2017 to 2020. Then we can see what this shows is the impact of the fires on the air quality. On the left, you have an example from here in the US in the California fires. What you see is the from the left is the satellite derived aerosol optical depth, and then the surface measure PM 2.5 during the fire events in October. So you can see both satellite and surface actually tracking the change which are happening in atmospheric concentration due to the fires during this. On the right, this is an example from India where we see the blue is your PM 2.5 mass concentration in Delhi, whereas the red is the number of fires which is happening in Punjab and Haryana from the VIIR satellite. And we can see that nice
Unfortunately,
almost one-to-one correlation between
when
these two.
you're
So this is very highly correlate. When there are more fires, we see high concentration of pollutions. It's not just the fires. There are other players which actually have play huge role, and we should always consider those players also. So there's a dust transport, local source emissions happening all the time, and then the weather all play their role. So what you see here in example is this is from yesterday's satellite image. You can see there is a system in the Arabian Sea. There's a dust transporting from the Arabian Peninsula here in Pakistan, in Afghanistan, Iran, and there are large number of fires actually happening in northern India. And what you see on the right is a forecast, 3 days forecast, air quality forecast. So you can see how the pollution actually from IGP is flowing in a specific path and affecting air quality in Rajasthan, Gujarat, and actually pumping over ocean. Similarly, the dust is coming out of this from the Pakistan and Iran here, and everything is actually getting transported again towards southern India and central India with the weather system. So it's not an easy problem, and it is very difficult to actually blame one player unless you consider all of them together. So just last closing slide, I just want to let everybody know that we have been organizing this community response forum this year to specifically to actually provide an update on fires and air quality during this specific season. Everybody can join, all the details are here. And then also another note I want to make is that we have this network of low-cost sensor which we are actually putting in Delhi and Punjab and Haryana this year to track some of this, fill some of the data gaps in the region so that we can have better measurement from the ground. And I think that's all I have. Thank you very much. Sorry about all the glitches.
Thank you so much, Pawan. And no need for you to apologize for the glitches. I think there's some combination of Zoom, internet, and transboundary movement of information that's not in our favor this Monday. I'd like to turn the spotlight over to Professor Mark Zondlo to speak about his work on a different kind of agricultural related emissions. And just in case you're not looking at the chat, for all the participants, after the three science presentations, we will have time for a brief Q&A on the science of agriculture and air pollution in India before shifting to the solution side. So thanks for bearing with us on the glitches, and thank you to Ipshita for performing multiple heroics to keep us all back on track. Over to you, Mark.
So I want to talk a little bit, and actually this is a perfect introduction to some of the work that I'm going to be doing. I'm going to talk more about trace gases and specifically talk about ammonia, which is a really important precursor species for particulate matter. And ammonia comes from two sources, mainly from agriculture, but of course biomass burning is also an important source. And then in India, it's mixed up. So trying to use the satellite data of ammonia, which is a relatively new approach, and try and constrain it. So I also want to thank Christopher Beal, a postdoc who's working on this project, as well as my collaborators, Fabian Pelot at the NOAA Geophysical Fluid Dynamics Lab, and Cynthia Randalls at Emory. So, and of course, we have the science teams from the various measurements of satellite ammonia. So we really want to, try and use the satellite data to constrain new emissions of ammonia. And we care about ammonia, like I said, because it's a precursor species. It actually plays critical roles in nitrogen deposition from an ecosystem science point of view. The main sources are, globally are agriculture, about 70 to 80%. Biomass burning is typically thought to be around 20%. And in cities, vehicles can actually be pretty significant sources of ammonia as well. It doesn't seem to show up as much as the prior two, but it does, based on in situ measurements, we do see an awful lot of ammonia there. The emission inventories are very poorly constrained, particularly over India, although that statement is true pretty much everywhere. There's no national ammonia measurement network in India. In fact, actually in Europe and the United States, that's only really come about in the past 10 years. So if we're trying to understand how PM2.5 forms by precursors such as NOx and SOx, we also need to understand where ammonia is coming from. So VINIAC actually has done some of the first in situ measurements, or at least some longer term ammonia measurements, but there's no easy way to get ground truth. So satellites provide a really interesting way to look at this. So what I want to show here on the right is satellite measurements of ammonia. This is for the month of January. This is a log. We're looking at a column amount, just like we talked about before. So the key thing are the yellow colors are a lot, and kind of the blues are nothing. And I will set this in motion. So this is January, February, March, April, and then you can see there's a shifting pattern of high ammonia over the northwest IGP. And then in contrast, in February and March, there's a much bigger plume of ammonia over northeast India and Bangladesh. So you see this very changing both space and time pattern, which suggests that we can't really obviously take India as a whole and just parameterize it, which is currently how emission inventories do this. So we can use satellites to help constrain this. So we can take the high resolution satellite images of ammonia, getting down to basically 2 kilometer resolution by doing a oversampling algorithm, where basically you give up temporal averaging, and for example, like I showed, take the entire month, but then you can get higher spatial resolution than the native footprint of about 10 to 20 kilometers. So the map on the lower left shows high resolution using combined YASI and CRIS satellites. And we've done the appropriate quality control because ammonia is a new measurement to do. Sometimes it can measure slightly different things, and we've done that. But you can see the seasonalities are shown in colors here. And I want to emphasize that again, over Northeast India, Bangladesh, you can see this peak like we saw before in kind of March and April, but then over more of the wheat growing region, we see a peak in July. So, you know, these are the dominant regions of ammonia, and yet we see much different seasonalities, and that has a big implication on PM2.5 formation. Now, if we take the continent as a whole and lump the subcontinent as to one data, you get a seasonal pattern where it just averages out. It's driven kind of by the Northwest India region. It peaks in July. The currently used emission inventories are based off of in CMIP6 model. And basically you can see it has a peak in spring and a peak in fall. Why is that? It's that way because that's the European pattern of ammonia. So we're taking European patterns of ammonia, and because we don't have much data, we're applying it to other parts of the globe, such as India, and we're going to get much different understanding of PM2.5 formation because temperature and relative humidity and other precursors change so much. So this shows a map from the Merca 2000 data set of wheat production peaking in summer, and then rice production. And these are the areas that, again, in this kind of where we see wheat, we see this peak in July. In kind of the lowland region, we can see more of our early, late winter, early springtime peak. And, so why is this? Well, part of it is fertilization. So again, here's that July. I just did a screenshot of July up here. You see this peak. If we look at fertilizer application, which is shown down here, you can see, there's intense fertilization right where you see the high ammonia. Same thing, a smaller peak, but still lots of rice fertilization in this time frame of late winter, early spring. But it's actually pretty complicated because nitrogen is applied many times throughout the year, days after tillering, days after seeding. So there are many times, for example, as to when you actually fertilize. And what's shown here are kind of the time frames that you often see it application. Now, this is not specific to this part of the country, but when you see fertilization happen. So it's only part of the story. And going back on some of the MODIS fire counts that we just heard about, here is a day with few, crop burning events. So these crosses are locations of fires. These dots are the individual daily satellite pixels. And you can see, on this day, we're working on the winds, but basically the winds were kind of coming out of the easterly and almost southeasterly in this region. And you can see where there's a fire here, there's some indication that maybe locally there's high ammonia, but then on days where you have massive agricultural crop burning, you can see the whole region has really high column amounts of ammonia. And if you actually take some of these individual examples, you can calculate with models, you can get the emissions of ammonia to carbon monoxide. So this is just an example to show what can be done to link satellite gas phase measurements with fire counts and even aerosol optical depth to get a much bigger understanding of what's happening. So satellites provide new promise for high resolution ammonia, both at the monthly scale and daily scale, which can be a top-down constraint of emission inventories. As we just heard, it's not, although the emissions scale pretty well, ammonia has a short lifetime with the maps of the ammonia. There are other processes that are going on at different scales going into aerosol phase. So although the scales with emissions, there are many other factors going on. The seasonalities in the CMIP6 are unlikely to capture what's really happening, both spatially and temporally. And certainly, crop burning is an important component of ammonia. And I think that's why those seasonal patterns are actually really hard to interpret, because it's a combination of fertilization, crop burning of different crops at different times a year. So with that, I think I've run out of my allotted time, but basically there are ways that we can, we just heard about the low-cost sensor network. There are ways that by having, and some of our colleagues, I think Vinayak will be talking about this soon, using in situ measurements combined with the satellite and really get a more complete picture from both a bottom up and top down. So with that, I will say thank you, and I look forward to the panel and discussions.
Thanks a lot, Mark. And I think one of the things that for non-experts in air quality, sometimes the idea that you can have two gases combined to form a particle is not the most intuitive one, but the importance of that for actually driving some of the particulate matter pollution exists, whether or not it's intuitive to us or not. So thanks a lot for that. With that, I'd like to turn over the spotlight to Vinayak, and then we'll pause for a brief Q&A after that on the science portion, and then move into some of the solutions. So Vinayak, you have 7 to 10 minutes, please.
Yes, very good morning to all of you in the US and good evening elsewhere in India. Well, I thought that because the topic was about some of the research and innovation that has enabled us to understand the air quality and air pollution sources at a more detailed speciation sort of more details of the speciation. I thought that I'd first start off with that. So this is a map at the bottom. You can see it just shows where I work. And if you would have paid attention to Pawan's and Mark's presentations, you can see this is really virtually the one of the hotspots of where the agricultural burning occurs. If you could please go to the next slide. So that region is really where you have rice and wheat cropping cycle, but just for the others, the work we do at our institute covers several themes. And here I just wanted to point out that, in terms of the complexity of what makes the smoke, what the smoke comprises of in terms of both gases and particles. Although people in Delhi and in the newspapers, most of the citizens are aware of particulate matter pollution from the source. I don't think that much attention has been given to the other toxic substances that are in the gas phase. And as Mark was mentioning about ammonia, in addition to ammonia, which can actually also form particles through combining with other gases, there are lots of other toxic substances in the gas phase. So just to complete on this slide, these emissions all, of course, enter the air. And then what starts sort of, if it's agricultural burning, it actually can come back to haunt the crops themselves and also affect the food security. So if you could go to the next slide, because I think the effects are well known in terms of pictures. Yeah. So in order to be able to address this at both a process-based level, mechanistic level of gas to particle conversion as it's occurring, and also in order to measure the precursors of PM2.5, because for most of the audience, I think it's important that we understand that PM2.5 is at the end of the day just a bulk parameter. It doesn't really tell you what the PM2.5 is made up of. Although we do have now some idea of chemical speciation, but really it's just a bulk parameter that's like a first level of screening for whether you have an air pollution problem or not. And then if you want to know about the consequences of exposure to that particular PM2.5 loading in the air, then you really need to know the details. So what we did in our place in IISER Mohali is we've set up a really great facility where you can measure a large number of these molecular traces that have information in them regarding both chemical processes and also, more importantly, the individual sources. So you have probably heard about DNA fingerprinting, most of you. And in the next slide, I'll show you how chemical fingerprinting of air pollution sources looks like. If you could just change to the next slide, please. So the previous slide was just showing you the different instruments that enable us to measure about 100 molecules or more. So here you see a picture of a person who's up to no good, but we don't know the identity of the person because he or she is wearing a mask. So it's pretty much the same in everyday phenomena where you see a smoke plume going up somewhere. If you can just click on the next sort of thing. Yeah, so you see a smoke plume like this probably. If you're lucky, then sometimes you can see directly the source of the smoke or the pollution plume, which in this case is this rusty old rickety vehicle. And if you know the identity, of course, then you can make your own designs of how to control that particular emission source. But what if you don't? So then if you click again, please. So here you can see, for example, if you can measure all these important molecular traces that have the information about the sources, and then you can you sort of arrange them in a particular sort of way of plotting, where you plot, for example, acetonitrile is one of the compounds on the x-axis, one of the axes of the cube. I think you can read that out. That's a very, very good chemical marker for biomass burning. So it's a molecule that's emitted when you burn wood or biomass, but not so much when you get traffic. And then you have aromatic compounds on another axis and oxygenated VOCs on another. But the main message here is you can really resolve these pollution plumes in terms of their sources if you can measure in this particular air mass all these other molecules in addition to your PM2.5. So this is really molecular level of fingerprinting. Yes, now you can change it to the next. So in this part of the world, the reason why you have a lot of biomass burning during the October-November season is because a lot of the paddy stubble remains on the ground. And in actually, what is not noticed that much by people in Delhi is there's also a fairly large amount of burning in April, May, when the wheat residues burn. But it's just that at that time, as Pawan was mentioning, meteorology is very important. At that time of the year, the air pretty much just rises up vertically and does not really come down over Delhi like it does at this time of the year. So anyway, so there's this machine called the combined harvester machine you see on your screen. And it's in fact, when this was introduced for mechanized harvesting, when this problem started happening in the 1985s, 1980s. And if you click again, so now in terms of post-harvest operations, it's not like there are no other alternatives. So if people choose to grow wheat right after the paddy, then indeed now Punjab Agriculture University in Ludhiana has come up with this happy seeder machine, which can actually sow the wheat right through the stubble, which means that the farmers don't actually have to burn the stubble or get rid of it from their field. And now if you just click quickly the next 3 clicks, please. So you can see that all those emissions, both in the gas phase and in the particulate phase, they actually then by themselves, they are toxic, but at the same time, they also are a very good cocktail for brewing secondary pollutants like surface ozone. And like PM2.5, surface ozone is also criteria air pollutant. And then you have a whole host of other secondary species that can be formed, like secondary inorganic aerosol and secondary organic aerosol, which is a large chunk of your PM2.5, both of them. And then the last picture on this, if you click, is simply that if the crops grow in this very polluted air, then they really undergo stunted growth. So the first picture is actually an example of wheat grown in Pakistan, Punjab. If you grow it in very clean air, you actually have very good productivity. If you just filter it for remove ozone from it, but leave the other pollutants in, that's the middle picture. The growth is somewhat stunted. But when you just grow it with ambient ozone, which is like just a few tens of ppb, you really, really see a remarkable change in the crop productivity. So what started with this agricultural management practice, which has to do with crops, actually can come back to affect the crop yields. Okay, so now we're all set with the background, and we can now look at some of the species I spoke about that really ramp up because of these emissions that occur due to agricultural burning. Can you go to the next slide, please? Yes. So here you can this is just a picture to show that there's a lot of fire activity that satellites can detect. Can you please click on the next? So this is October-November season. Can you just click to the next slide? That's the spatial extent. Just keep going. So here you see the chemical data organized in terms of the pre-harvest and post-harvest. I think I'll make this the last slide because it gets across the message. And you see that acetonitrile, the very first panel, if you go back, it's a little bit crazy. Yeah, so acetonitrile, the red markers correspond to the ambient measurements when the fires are active, and the blue ones when you don't have the fire activity, but it's very similar meteorology. And what I'm showing here is that you have a molecule called isocyanic acid, which is a close relative of methyl isocyanate, the gas that was leaked out in the Bhopal gas tragedy. And you see that it has both a daytime source, so it's being photochemically formed, and it also has, during the fire affected periods, an evening time peak, which shows that it's also a direct emission from the fires. And actually, this is very toxic because it can impair certain proteins that are involved in eye vision and arthritis. So I think I'll stop here because I'm at the end of the time. But my main message was simply to tell you that there is a lot of other ambient air pollutants in the gas phase, and not all of them are direct emissions. There are many, like Mark was mentioning, which can combine together and then add to the PM 2.5 burden. And they're not nasty. They're pretty nasty stuff to breathe in. So I'll stop here.
Thank you, Vinayak, and thank you to the panelists. One of the reasons that we had assembled this panel was actually to take advantage of the moment of people being very concerned about agricultural burning, but also point out that the spectrum of ways in which air pollution is formed from different agricultural activities is broader. And many of these points also deserve considerable policy attention. So just one quick thing is that there are a number of questions that are coming up in the Q&A. One of them from Tina Chada is, I think, the question that's on many people's minds right now, which is, what is the percentage of overall air pollution that's derived from agricultural burning versus other air pollution sources? I know there's been some back and forth in the media on that point. And I'd love it if the panelists or maybe Pawan can start with a discussion of what's known and not known about that percentage.
Thank you, Jessica. So I think that is very difficult question to answer when there are multiple things you have to consider when you say where, in which place you are trying to see that contribution, either near the source or away from the source or several hundred miles away from the source. And then the second is at what scale? Is it we are talking about an annual scale or on a given day? So far, based on studies, based on our own model simulation, what we have seen is that on annual scale, the contribution from the northern India agriculture burning typically is about 20-25% on an annual scale in cities like Delhi and downwind. But on a given day, that can change frequently. It can be 5%, 10%. It can be factor of 4 or 5. And we have seen such examples in last 5-10 years where we have seen multifold increase in pollution just because there are favorable weather conditions, favorable winds, number of fires were burning large amounts. So it's still, I think, still we don't understand all the players there. And like Mark mentioned, the emission inventories are not very well designed for other pollutants. It's very, very difficult to separate that signal yet. I think other people might have comments.
So there was one quick follow-on to that point, the difficult to separate the signal, and that was from Sandeep at Ministry of Environment and Forests on what is the height of the smoke plume from agricultural burning, and does aerosol optical depth, is that able to provide some input in this regard? So if others have comments on this separation.
Yeah, Jessica, just before that, I'd just like to add to what Pawan was saying. So actually, it is true that for this current year, 2020, we still don't know what, it will take analysis. But for 2018, there are already many studies, and some of which in which my group also participated. And there, the specific question, I think your question was, how much of the pollution at this time of the year in Delhi can be attributed to stubble burning in Punjab? So from 1st of October till 1st of December 2018. So we published this in Environmental Science and Technology this year, and this was a national team effort. The number comes out to be the seasonal average is not more than 20%. And as Pawan was saying, yes, some days you can have really nasty plumes, but the seasonal average is just 20%. And I think it's important for people to recognize why this is so. because you see these large fires, and of course there's concern, there's so much being emitted. The reason is because in September, the ventilation coefficient during the monsoon season over much of North India, including Delhi, is somewhere around 1300 meters square per second, which is essentially the rate of removal of pollutants, if you will, for people who are not familiar with this. And this, by the time you reach October, November, this gets reduced by half. So it's down to around 600 meters square per second. So what this essentially is saying, that even if you would not have, of course, there is some addition to the pollution in Delhi from this 20% of day-to-day variability of few percent. But even if, let's assume that there is no burning, just the sources in and around Delhi would actually lead to ambient concentrations doubling up, because the removal rate has slowed down. We're transitioning to winter. There is less photochemical removal, although there's also some production. But the main thing is really the ventilation coefficient. This really gets hard. So I just wanted to register this point, and that paper I can send to you, which you can then share with the participants.
Great, thank you so much. And there's one other kind of cluster of questions that I wanted to make sure we get to before we move into the solutions. And kind of a representative set of these questions is from Madhur Kotare. And the question is, what is the view on PM 2.5 as the physical part of pollutants? And what they're asking is whether it is the 2.5 micron or the much smaller particles that are the ones to be concerned about. Are we worrying about wrong parameters? Should we be looking at other gases and other parameters? What should we be concerned about? And for what do we have data? So small questions. And I wonder if the panelists could say a few words about tracking what to pay attention to and what to be concerned about. And also some of the emerging potential for gathering data on those points.
I can take very broad view on that. Definitely, most of the health studies have been focused on PM 2.5, and the reason is we have the data actually available. But there are a number of studies which suggest that actually the finer, the smaller the size the particle, it can reach to the different parts of the body more efficiently and deeper inside. Like there have been studies, medical studies, where people have found the submicron particle in human brains. So I think smaller the particle, there is a more risk. And PM 2.5 is definitely one of the parameter for concern. Unfortunately, we do not have more measurements for the finer particle to draw more conclusion on that.
Thank you. And I think that's, and I want to take the opportunity at this point, since we have both expanded the range of emissions to worry about, expanded the range of pollutions to be concerned about, highlighted some of both the agricultural as well as health effects, to shift gears a little bit and to talk about solutions, some of the things that we can do to reduce these emissions and consequently the impacts of ambient air on both rural and urban people as well as plants. So with that, what I'd like to do is switch to the second part of this webinar and ask Ms. Preeti Kumar to turn the spotlight over to Preeti to talk about some of the solutions that are both new and old and known about reducing agriculture-related emissions.
Thank you, and good morning and good evening to everybody today at the seminar, depending on where you are in the globe. I'm Preeti, and I'm very happy to be presenting and being with all of you today. So we are part of the agriculture team in the India World Bank office as part of a broader air quality management endeavor that's being led out of the Environment, Natural Resources and Blue Economy practice, but it's very much a multi-sectoral kind of initiative. For the past couple of years, we've been quite deeply involved as part of the work. And I'm sort of happy to let you know that we're still learning ourselves and, tell you about some of our perspectives. So my mandate today was to talk about not the science part, because we had 3 experts talk about it. They've set the stage on 2 aspects, crop burning and on ammonia pollution, and the latter coming primarily from the fertilizer sector. Today, I will be speaking about solutions, both technical, including some policy aspects, Let me also say at the outset that I was hoping Professor Gulati would have set the stage with a much more profound and a more overarching sort of policy framework that would have made my job much easier. But nonetheless, I will try to provide you with an overview flavor of issues on the technical solutions and policy. So the key messages I want to leave you with in general over the next 5 minutes is that the issue of air quality, as you've seen, is about particulate pollution and other pollutants, ammonia pollution, but there's also issues around soil and water. So it's a kind of a nexus. And India is facing a very deep nexus issue, which you cannot disentangle one from the other. So solutions for air will lie in the agriculture sector. And the IGP has been very rightly sort of made prominent in terms of the geographical space that needs to be addressed. Air quality, big burden of disease, soil organic content. India's soils are dying, to say the least. The organic content is at 1% or less. As per experts and recent data, the critical threshold for soil to be active for productive growth is minimum 2%, 1.5 to 2%. So you can get a sense of where we are. And a lot of crop residue burning, CRB, fertilizer use have very large sort of externalities on soil nutrients. Our soils are brittle, on ammonia pollution in the air, which leads to a lot of particulate pollution as well. A lot of technical options have been identified. I'll let you know about that in a few minutes, but there are knowledge gaps. The answers aren't fully known. You'll see that in these various options, there isn't enough done yet in India on the environmental footprint analysis of these options. Which options are more economically viable that India should take on in the long term or even in the short term? We don't see a lot of economic analysis there. And scalability, which ones we don't need pilots in a country as large as India. So scalability assessments are also important. And this is where institutions like the World Bank begin to play a much more important role in the dialogue, in our sort of assistance to the government of India and the state governments. And an important concern broadly, I want to lay out that there are short-term solutions, but short-term fixes should not compromise the longer-term desirable outcome. And the desirable outcome has to do with the nexus that we had talked about. The second important slide, and this is a very interesting one we came across recently. This hasn't come out of World Bank work, but it has come out of the consultative group of the International Agricultural Research, the apex organizations in the world right now on ag research. Basically, this slide says, and there's a, you can see down below the source, the slides in a very kind of late term basically says that in 80% of India's global warming mitigation potential comes from 4 or 5 low-cost measures. If the agriculture sector starts employing more efficient use of fertilizers, zero tillage, which is a conservation agriculture practice, there are innovative ways to manage water within intensive rice systems, rice water management. And if you eliminate crop residue burning, India will be successful 80% in reducing its mitigation potential. So just to let you know that crop burning and fertilizer use has huge sort of global commons effect. It's not just a local problem for India, but we can do a big job in terms of addressing the global issues. Now let's look at crop residue burning in the long term. It's an issue where I think it was mentioned by Pawan, and it's now very well known that it's prevalent in all of India, right from Bihar to Jharkhand to southern India. But of course, you've got some big spots up there in northern India. And the northern India parts of Punjab, Haryana, Western UP were entrusted with our food security, which they've done a great job over the last few decades. But now the solutions lie in diversification. The long-term solution is to take parts of India away from the rice system. There's a broad consensus around the discourse here, but the political economy, the political will is very, very difficult, because then comes the question of the farmers' welfare. How do you strip farmers? How do you strip the farming systems from the whole rice system, which it has been doing for decades? Is there a way to do it through policies? There is a minimum support price right now attached to the rice wheat system. Can that be removed? Can that be changed? It's very distortionary. Farmers will just keep doing this and nothing else, right? And it takes up a lot of groundwater. It's resulting in crop residue burning. The soils are, soil health is going down. So the answer is yes, you can do a decoupling of the procurement and take away the procurement to, say, the last point, shifting the public distribution system paddy to Eastern India, say to Chhattisgarh, to Bihar, to Jharkhand, where water is abundant. And that will take away rice from parts of India. Ones are those, for example, the maize wheat system is a possible one to do as well. So in the long term, diversification out of rice is necessary. And the CRB, in especially Northwest India, is really a consequence, as somebody mentioned, of the monocultural rice wheat cropping system. The last point is, I have mentioned that on the minimum support price. Now, you all might have questions about how easy said than done. Well, yes, easy said than done, but there are solutions here around cash transfers and cash incentives that can be done in overexploited areas. Now, in the short term, what can be done on crop residue burning? You've got laws and regulations in place in India. Enforcement is improving. As you know, the Supreme Court of India, the Green Tribunal, all of them have banned now crop residue burning. You've got quite a command and controlled approach that is currently going on in Delhi, in other parts of India. So enforcement is improving, but how good is enforcement going to be is really needs to be seen. It's not a very sustainable option. But broadly, solutions in the short term are in these categories. One is in the agriculture system, primarily, there is a time when farmers will sow and when they'll harvest. And this time period depends on what duration variety of rice you used. Most traditionally, farmers in northern India have been using long duration paddy varieties, which basically leaves them with exactly about 15 days before they can sow the wheat. So they just they light a fire and burn the field, right? So the idea is to move away to lesser duration varieties. Farmers sow early, they harvest early so that they have more time to prepare the Rabi field preparation. Will that reduce crop burning? Well, it may or may not, but this is definitely an area worth moving towards, and it has co-benefits on higher yields. And I must say, ICAR and the Punjab Agricultural Universities are absolute champions in this area. This is not new to India. This has been going on, but now new research in the last couple of years is coming about here. Another innovative thinking is around combined harvesters. This is an imported technology really suited for countries which had single cropping systems. Can the combined harvesters be improvised for India's farming systems, where you don't leave behind a feet of stubble? And can the private sector come in with farm machinery solutions here? This is something that even we are very interested to kind of explore further. The third and fourth bullet points is on-farm management of residues. A lot of this is already happening in India, particularly in Punjab and Haryana. This is essentially putting the biomass, cutting the crop residue, putting it back into the farm. Don't take it away from the farm, put it back into the farm. The more biomass that you put back into the farm will improve the soil organic content and its productive capacity. And as I said in the beginning, India's soils are dying. So this is any solutions to crop residue burning should also improve soils. And finally, you've got a lot of energy researchers, any energy practitioners saying, how about we take the residues out of the farm, off-farm utilization, and you attach a financial or a monetary value by converting the residues into bioenergy. And this is another solution that's being promoted. But of course, what I want to say here is that lessons of India's work, Government of India has done a lot of work on bioenergy, and the lessons from all these programs should be taken into account. And there are certain considerations on the trade-offs between short and long-term desirable options. In situ, you have to look at technology options, but the versatility across different types of crops. So the technology should be agnostic to crops, as well as your enterprises and industry should be agnostic to the raw materials when you take them for conversion. This is an interesting economic analysis, sort of, not very sophisticated, but just to let you know that from the economic analysis shows that the red is the burning option. And if you go towards the light green option, which is putting the biomass back into the farm, is by far the most economical option. If you see the dark green bars, they represent taking away the residues out to some external area, converting it through industries and enterprises into biochars or briquettes and things like that. And the economic viability, as per some economists in Punjab right now themselves, is showing that it's not viable. So the economic viability of solutions needs to be determined and assessed before any solutions are rolled out in a certain manner. India doesn't need any haphazard solutions anymore. Finally, we talk about ammonia pollution. What's the thinking on that? This is an area that we are trying to get into in the India office of the bank. It's as Mark and Vinayak pointed out, a particular area of concern for India, not well recognized, but particular area of concern because we are amongst the largest countries in the world using a huge amount of fertilizers. There's a whopping amount of roughly $15 billion per year that India spends on fertilizer subsidies to its farmers. And we also have one of the largest livestock sectors for large ruminants that also contributes to methane and ammonia emissions. What can be done about fertilizers? So nitrogen-based fertilizers, urea that's used in India, it's very kind of imbalanced. As some of you may know, the ratio should be 4:2:1. In parts of India, somewhere close to 40:8:1. Completely imbalanced because of the fertilizers subsidy that farmers then get incentivized to use more and more of the N part. And so the idea is that, and you know, Professor Gulati and people like him, who are the real gurus in the fertilizer kind of sector, have been talking about decontrolling urea, decontrolling the fertilizer sector, where now India needs to move towards more market-linked urea prices. Just like you have the NPK, the P and K is not subsidized as heavily as urea. So it's more kind of market-linked, and that will sort of disincentivize farmers to use excessive fertilizers and over a long period of time reduce the overuse. So the policy dialogue is complex. It depends on the political economy and the political will, but there are some solutions. And finally, on the short term, there is certainly a progressive sense within the government to do an improved targeting through DBTs, bringing fertilizer efficiencies. If farmers get the right fertilizers in the right amount, there will be lesser wastage, lesser pollution. And finally, there are other technical solutions around, deep in the agriculture sector, which is you can do neem coating and you can do rice, alternate wet and drying, conservation agriculture. All of this will help to improve yields, help to improve the nitrogen use efficiency. The absorption capacity improves, and nitrous oxide pollution will reduce. Similarly, in the livestock sector, there is work in a large livestock program that I know of the government of India, where they have done some ration balancing programs that shows that methane emission can come down. So as you can see, I'll stop here. That was my last slide. The solutions are quite complex. It's a combination of technical and policy solutions. The policy solutions have a complex political economy, but there are lessons from the international experiences. And there is a dialogue going on with the Ministry of Fertilizers, with the Ministry of Agriculture, but much of this on the policy side requires a much deeper discourse and a multi-sectoral dialogue to take forward. And of course, on the short-term side, I think we're already doing very well in terms of the research on technologies. And as I said, as I close, more economic analysis and scalability assessments need to be done before we can roll out any thing in a very haphazard manner. But overall, these are my sort of overarching points. Thank you very much. Over to you, Jessica.
Thank you, Preeti. And I think one of the things so Preeti had pointed out that the solutions are complex, but in some ways the complexity is more of a governance complexity than an individual set of solutions, because everything that's mentioned is doable. It's just a lot that needs to be coordinated, evaluated, and figuring out what is the most cost-effective way to address multiple emissions. I'd like to turn it over to Jostein Nygaard to speak about briefly on some of the governance frameworks that can help coordinate and organize the different types of sectoral and analytical actions that it will take to be able to marshal all of these individual contributions to better air. And then we'll conclude with about 10 minutes of Q&A at the end. Thanks. Over to you, Jostein.
Thank you very much for inviting us from our institution to present here. Yeah, so we have, as Preeti mentioned, we are actually working quite extensively on how to cope with agriculture-based pollution for now over the last several years. I have to say that the knowledge about agriculture sources and how it impacts the air quality is not necessarily something that have been around, that the knowledge have been around for a long time. So we are really also still in the piloting mood here. And we started actually the first substantive engagement to control agriculture sources, I would say, and particularly the formation of secondary particle over the last 5, 6, 7 years, where we particularly were drawing upon US and European experiences that we brought into China and now increasingly to India and the South Asia region. So just very quickly, the others have done better presentations than me on this. And Mark was showing also the formation of PM2.5 also continuously through the year, but just some yearly averages here. You will see to the left that the overall concentration of PM2.5 in the overall South Asia region really is concentrated around the Indo-Gangetic Plain. What you see here to the left side of the figures is really the high concentrations from natural sources, particularly coming in from the Arabian Peninsula, Iran, through Pakistan, and then have impacts in the western and southwestern part of India, while the anthropogenic sources at the yearly average is much more on the Indo-Gangetic Plain, from Pakistan to India and into Brahmaputra, Bangladesh, and so on. So here, basically, if you take the yearly average for the region, you will see that from the primary sources on the left-hand side, it's again really a focus on the large Indo-Gangetic Plain. And here you will also see that somehow the peak values that probably contribute most in some of the areas of the plain is from prime sources, while on the other hand, the formation of the secondary particle that you see here to the right, it's more throughout the India. So where, for example, ammonia and the formation with NOx and SOx is transported over substantively larger areas, which is a phenomena that we are used to from China too. So you somehow need a large regional control program put in place in order to control the secondary formation, as you see on the right-hand side here. And also here, if you look at the fertilizer use and livestock over main or finding here on the left-hand side is really again the focus on the large Indo-Gangetic Plain area, and then a little bit more localized focus on part of the Indo-Gangetic Plain area for the agriculture crop residue burning sources. Now, the critical tool that we are using when we have our dialogues with the government partners is really to do these presentations here where we look at what are the contributions from the various sectors. So the left-hand side, the example of the entire Bihar state, which is right in the center of the Indo-Gangetic Plain. You see basically the sector contributions from household, from transport, from different industries, power plants, and so on, and that most comes from inside the state, but also large contribution from the neighboring state, and so on, further to the national level, and so on. Now, on the right-hand side, you will then see in the gray here how much comes from secondary sources. And in general, our picture is, for Indian state, that about 50% of the concentration levels are formed through secondary particle reactions where particularly agriculture sources reacts with NOx and SOx and so on from industry, energy, transport, and so on. Now, then basically the agriculture part, one is more the primary concentrations that are caused by primary sources, where we have the agriculture non-residue burning. And then basically we see here this substantive reaction pattern coming from agriculture, transport, power plants, industry, and waste forming the secondary particle part. Now, what are the solution models we have, and what are the technologies? Preeti already talked very well about urea and an application of urea like the neem coating that is being applied in India. Other parts, is to get the fertilizer into the soil substantively, so you get less ammonia emission. Another part here really is focused on the manure part. What our findings is that probably manure contributes even more to the ammonia emissions than fertilizer, at least in part of certain geographic areas. We are still in the middle of studying further the manure contributions to ammonia in India, but the application that is usually being applied is to improve the storage of manure, cover the manure, and improved application of manure. Mostly this is done in large and medium-sized farms, so we need to somehow get a better understanding of the contribution also from medium and smaller farming in India. A new technology that also is being developed now is the plasma reactor technology that's convert the liquid manure to solid fertilizer and thereby also eliminates or at least reduce substantially the ammonia emissions. So here are some of the technical solutions. Now, if we look at the cost effectiveness of the agriculture-based sources or interventions, what we learned from the China case is that basically they focus on the industrial processes, power plant control, switch to clean fuels in households, and so on. And these were the main, as you will see here in the dark blue, were the main applied interventions that was applied in order to get the substantive improvements surrounding Beijing and in Beijing over the last 5, 6, 7 years. Now, what we also learn is that when we look at the measures to apply in over the next 5 years up to 2025, that the urea fertilizer substitution, increased fertilizer use efficiency, and some of the manure management like from pig farming also can play a substantive role in order to achieve results in the years to come. So in the case of Hebei province surrounding Beijing, we basically with the current plans, you can see that you can reach about, we estimate about reaching about 54 micrograms per cubic meter average concentration value by 2025, which is a huge, it's almost halved the concentration level surrounding Beijing over the last few years, and then we add the next 5 years, we will come down to that level. Now, if you look at the various abatement options we have to further improve the air quality, with let's say about 14 to 15 micrograms per cubic meter, we see that increased fertilizer use efficiency, urea fertilizer substitution, go into manure management here, further manure management and so on, becomes critical abatement options that have relatively good cost effectiveness if we compare with some of the more traditional sources. So to conclude here, what we basically see is that the abatement measure for agro-based air pollution are often developed after the traditional measures have been implemented and then being applied. That's somehow the current pattern we can see in the countries we are working on air quality. But when abatement technology and cost effectiveness are known, we can see that the ammonia management could often be applied earlier in the AQM planning and implementation process. Many of the ammonia management measures are cost effective, as we can clearly see from China and Europe. However, and this is critical, we need to better understand the contribution of PM2.5 concentrations, and particularly from manure part to further define the options of cost effectiveness for ammonia management, particularly in the medium and smaller scale farming, where we only have a limited knowledge. We are in the process of building much more extensive understanding of ammonia monitoring in India. We are integrating this into the current expansions of the continuous ambient air quality monitoring networks. And one of your participants also asked for finer particle concentration monitoring. We are working on this, integrate this also in the expanded ambient air quality management network. So also the cost effectiveness of ammonia management is an important part of the overall air quality management tool development we are working on now for the entire Indo-Gangetic Plain area. Thank you very much.
Thank you, Jostein. So just very quickly, because we have about 1 minute left. First of all, many apologies for not having a policy Q&A after this, as well as the science Q&A. But I think that the presentations that we've seen have highlighted both the complexity of marshaling the many activities that need to come together to reduce agricultural pollution, and also hopefully expanded all of the participants' sense of what are some of the emissions and activities that we should be considering. I think as a takeaway, as the moderator of this panel, and thank you very much to the panelists for joining us and to the participants for soldiering through some particularly tough Zoom issues this morning, is that we will have a follow-up podcast on air quality governance and how to bring the analyses, the data collection, the regulatory authority, the public investments, and the policy shifts together in a coherent framework. This is a challenging question. It's not an impossible question. And there are some models that various social scientists and policymakers across different ministries in India, as well as at the state level, are making some important progress on. So I think that'll be our follow-up to this panel, and we'll make sure that the materials from the panel, as well as answers to some of the more specific technical questions that came up in the chat, do go out to those who have registered for the webinar. With that, it is 11 o'clock and 9:30 p.m. And so thank you very, very much to everyone who was able to join. And Dr. Gulati sends his regrets. There was a connection issue in being able to join, but in any case, have a good evening, have a good rest of your day, and we will be in touch. Thanks a lot.